remind me at the end after I turn the recording off to ask about your weekly wins. Couple of things. Quiz corrections due in 2 weeks. The last day for you to turn stuff in for marking period 1 anyway. So, obviously, if there are extenuating circumstances, we can discuss it. But if you could try to get them by October 24th. Generally speaking, if the point of the corrections is that you have to do more work than if you just got the answer right in the first place, right? So make sure that you are giving me a complete enough answer that you're convincing me that you understand it and that your answer is correct. You have open internet, open book, open study guides, open whatever. And if there's something that you're not sure about, you can ask me and I will not give you the answer, but do like what I just did with the orbital question, like, kind of try to jog your memory or point you in the right direction, okay? You can get up to 100% coming back. I won't give you the points if your new answer is wrong or not adequately explained, but I'm looking for excuses to give you points, right? Second thing, the release forms that you picked up. This is not about you, it's about me. I am trying to become a national board certified teacher. And this process, it's a multi-year process that I have to go through that involves submitting a lot of data and student work samples and all kinds of other stuff. And also in one of the components, the one I'll be working on mostly this year, involves videotaping classes. So I will be videotaping this class. The release form is allowing me to include you in the video. It is not going to be seen by anyone except the moderators of National Board who have no idea who you are, and I'm not even allowed to put any identifying information about my school district on there, myself, and potentially Mr. Roberts and Ms. Islam, who are also doing this component this year, and we're all kind of trying to work together and check each other's work and stuff. So those are literally the only people who will ever see the videos. It is not at all evaluative of you in any way. It will not be shared in any public way whatsoever. It's really just about somebody else from somewhere else in the country evaluating me. My plan is to have a video camera set up often, partly just to do tech check and make sure it's working and that I'm getting sound and I can see the right parts of the room. And there will be times when I'm recording, or you might not even know that I'm recording, or it might be up and not recording, but it's partly to get myself used to having the camera around, and also you get used to having the camera around. And I will pick later which things I'm actually going to submit. So I don't even know on any given day if this is the thing I'm going to send in to anybody, and if anybody besides myself is going to see it, okay? If you would like to not be in that video, regardless of all of that, you absolutely do not have to, and you just don't give me the form, okay? And I will arrange the room and arrange the position of the camera so that you are not included, okay? So that's how that works. So if this is, if this makes you anxious at all or anything like that, don't give me the form, and also maybe just let me know so that I can prepare for that with, camera arrangements, seating arrangements, whatever, okay? But I want this to be as pain-free for you as possible, so that I can get the most out of it as possible. So I appreciate it if you, under consideration and discussing with your parents, can get those forms back to me. And don't be surprised when you see a camera in the room. Any questions about that? Okay, cool, thank you. All right, this is something that I linked for you in Canvas. This is by it's really just a guy, but it's his website is Compound Chemistry, or compoundchem.com, and he does these amazing visuals for a lot of different aspects of chemistry, and it's just sort of to be a public-facing, why is this the way? Very many of the paint pigments that you will find, and glass, stained glass pigments and other things like that, are because of transition metals. And it has to do with absorption of light and release of light by the electrons, just like the emission spectra, absorption and emission spectra that we were talking about earlier. Okay, except that instead of jumping energy levels, it's jumping levels within the d orbitals, which you might be like, but I thought all the d orbitals were at the same energy level, and they are, except when things come in to distort that energy, when things are coordinated around the transition metal atom or ion. So we have these things called coordination complexes or coordinate bonds. You can have a coordinate bond that's as simple as within an ammonium ion, the lone pair on the nitrogen finds a hydrogen ion, and that lone pair is considered an electron-rich area, and we'll talk more about that when we get into organic chemistry. The hydrogen ion has no electrons, and so rather than each player bring an electron to the table and share them, like in sort of a traditional covalent bond, the nitrogen is basically donating both of its electrons to this bonding situation. And so that's a coordinate covalent bond, but we can also have these coordination bonds or complexes that are more ionic in character, where we have something like an ammonia molecule where we have a nitrogen with electron-rich area where the lone pairs are, kind of donating, sharing its that electron-rich area to an electron-deficient transition metal. So this is, what you'll find is these things called ligands on the outside and the transition metal in the middle. It actually doesn't have to be a transition metal that you might have seen from one of the websites I showed you. You can see this like in aluminum. But there has to be space for those electrons to join and bond with the transition metal, which is why it's common in the transition metals, because they have flexibility in their d orbitals and of move electrons around depending on the circumstances. And so that's why you mostly see it in transition metals, or that's where a lot of the coordination chemistry comes from. And depending on the ion and a bunch of other things, you can have different arrangements of ligands around a transition metal ion. So you can have what's called a tetrahedral arrangement, which is very similar to a tetrahedral shaped molecule that we studied in honors chem. You can have other arrangements as well. This is the largest one, is called an octahedral complex. This is where we have 6 different ligands around that central ion. We're going to look at these sort of larger extended octet situations in covalent bonding as well when we cover that. So these last 2 are not things that you covered in honors chem, but we are going to talk about them in terms of regular covalent bonding between nonmetals as well later. But the idea is we can have different numbers of ligands around a central atom. We can also have different ligands themselves that have different amounts of what we call field strength that affect the central ion differently. Okay. So just as a quick example, this is an energy diagram of our d orbitals in a sort of theoretical crystal field, and then if there are 6 ligands in an octahedral shape around it, we see this splitting of the d orbitals into lower and higher energy. And that is really all you need to know. There's actually a lot of complexity behind that. And I will link to you the website that I got these images from that goes into it in a lot more detail if you're interested. But really all you need to know is when things surround a transition metal ion, those d orbitals split, forming a lower and a higher energy version. And then we can have transitions between those lower and higher energy states for the electrons, where they absorb energy and move up, move down and release energy, just like we've talked about before. And the amount of splitting depends on the shape. So tetrahedral splitting is going to be smaller than octahedral splitting. It's also going to depend on the characteristics of the ligand. it actually gets a lot more complicated, okay? This is an image from a different site that kind of gets into this in more detail. This was one of the things that kind of blew my mind in inorganic chem in college that I definitely needed to go into office hours for. But we're not going to get this complicated, okay? But what this does do, these transitions of the electrons between those d orbital energy levels is what creates color, okay? So the distance between those, the emissions from the downward transitions tend to be in the visible range. Okay, so we can see those transitions as wavelengths of light that are either emitted or reflected or like not absorbed, not emitted so much in a fluorescence kind of situation, although that is also related to this kind of thing. And you see this color wheel, it's a little bit, it might be a little bit different than color wheels that you're used to in terms of what are complementary colors, but this is in terms of absorption and emission, and you have something like this in your data booklet. Okay. It turns out this also matters for magnetism, because depending on how the electron arrangement when we have these split orbitals, we can have more unpaired electrons or fewer unpaired electrons. So if we have a small distance between them, it might be easier for Hund's rule to be in effect and say, all right, we're going to go to the higher energy level before we pair up in the lower one. But if as the orbital distance, it becomes more favorable to pair up down here than to jump up to the higher level. So that these coordination complexes also affect magnetism of a particular transition metal ion, because having more or fewer unpaired electrons is what creates that. Okay. And that is all I wanted to talk to you about. I'm going to stop here.